Hi everyone! In this video I will be showing why during a solar eclipse the path of totality is not wider than the moon. The first thing we need to understand is how the sun works, and I am going to show you two common models. The first is the way most kids think the sun works. It is a ball with a light bulb in the center shooting light in all directions. That's why kids really try to avoid the sun rays intersecting each other. In this model, the size of the sun doesn't really matter, since all light comes from the center. And it makes shadows similar to a flashlight. The shadow gets larger as you move the object closer to the light source. You can check this out here with Mercury. As we move it closer, the shadow on the other side gets a lot bigger. So now I want to show you how I simulated the light on both models, and I use lasers like this that are blocked by any object in the model, except I put a bunch of them together and tilted them +1 degree, -1 degree until I get a dispersion like this. So it can create partial shadows or full shadows and so on. The reason I limited it to just this angle is that I don't want my computer to die. And it is already pretty slow, as you can see when I move it around. In the second model, the sun works like a ball with many light bulbs spread across its surface. Each point on the surface is shooting light in all directions, much like a fire. Since in this model the light sources are on the surface and not in the center, the size of the sun affects the outcome of the model, as you will see later. In this model, if you put a small object in front of the light source, it doesn't block light in the same way. Much like in the tree in front of the fire below, does not block all the light from the fire, unless you put your nose really close to the tree. As you move away from the object blocking the light, the umbra, which is the shadow of total darkness, gets smaller and eventually disappears. That's why when Mercury crosses the sun, it never creates an eclipse, even if it is aligned with the center of the sun. So in here we can take a look at how the shadow from Mercury works on both models at the same time. And as you can see, they are completely different. But for now, let's put Mercury away and focus on the Earth, on the first model. And as you can see, the shadow of total darkness is larger than the moon. And either you are in it, and when you look at the sun you do not see anything, or you are out of it, even by a little margin, and you can see the sun just as you would any other day, since none of the light beams in that area are blocked. Now, before we zoom in on Earth, on our second model, it is important to notice this little detail here. I made all the light rays blue, except the ones on this area, which I made yellow, and it is going to be relevant in just a bit. So, as we zoom in, we can see that the shadow of total darkness, the umbra, is smaller than the Earth. And if you are in this area and you try to look at the sun, you will see a full eclipse. You won't be able to see the sun. But if you are just outside of it, in this area, you are going to see a partial eclipse. That's because some of the light rays will be reaching this area, but some that won't be able to. Like the yellow rays that I mentioned earlier, some of them are blocked from the sun in this area. So you won't be able to see the whole sun, you will see a partial eclipse. And this bit here is called the penumbra. It's the bit where you go from 100% darkness to 100% light, and it's a gradual change. It could be like 90% here, 50%, 20%, and in here you just don't notice anything because you can see the whole sun from here. So the last thing I want to show you is that this second model does not always predict umbras that are going to be smaller than the object. If we move this away and we find an object that is larger than our light source, then the shadow cast by the object, the umbra, from the object is actually going to grow as you move away. I hope it all made sense. Thank you for watching. And if you want, check out the video where I show this effect in real life.